Here our project title is single phase grid connected solar PV systems. Here we need to connect this single phase grid to our solar system. But grid is in AC nature, nothing but alternating current nature. In solar we are getting the DC output, okay, but this DC is not a constant DC. It is changing with respect to of irradiation and temperature. So based on this irradiation and temperature, we are getting the DC. If you take the morning 6 to evening 6, the output of solar panel is like this, okay. From morning to evening, sun temperature is gradually increases and get its peaks in afternoon and gradually decreases, okay. This is the graph. So if like this behavior, sometime you will get the high voltages and sometime you will get the low voltages. But our grid want a constant supply, right? So to meet this constant supply, we need to connect a buck boost converter, okay. Why? Because if we having the high voltage, we can operate buck converter to decrease that voltage. If we have the low voltage, we can increase the voltage by using this boost converter. That's why I am taking this buck boost converter to maintain a constant supply to the grid. But the thing is, the output of the solar panel you are getting DC. After buck boost operation also you are getting the DC. But this grid want AC, right? So to convert this DC to AC, we need to connect a inverter. By using this inverter, you can convert this DC to AC, right? So that is the point why we need to connect a inverter in solar panel to grid operation. And to give this AC supply to our grid, we are using the transformer. That's it, okay. This is the normal grid to solar connection. But here the problem is we are converting the power in so many stages. Here we are using the buck boost converter, and here we are using the inverter, and here we are using the transformers, okay. So here we are using the number of stages, means here we are using the 3 stages, okay. If stages increases, then device also increases, right? If devices increases, then switching losses also increases and size also increases, then gradually efficiency will decrease, right? So to reduce these stages, we are implementing a new technology, that is nothing but this single phase grid connected solar PV systems with a new, nothing but the novel means new, novel single stage. That is the meaning of single stage. Why we are using this word, okay. Single stage means here in conventional, in old technique, we are using the number of stages, okay, to convert this DC to AC and give it to the grid. But in our project, we are using the only single stage, okay. In only single stage, we are getting the buck boost and we are getting the inverter operation also, okay. That is the main thing. So single stage buck boost transformerless inverter, this is also main thing. So actually if you see the transformers at outside, it is like a big size, okay. So and it's also take a more space and loss also increases. So to eliminate that all things, in our project we don't take a transformer. So our project is completely transformerless inverter, means in our project we don't have this transformer. So these are the main reasons why we are taking this project. So our title is single phase grid connected solar PV systems with a new single stage buck boost transformerless inverter, okay. I think you will get the each and every word definition why we are taking here. Now let's look into our circuit. This is our proposed buck boost transformerless inverter. In this circuit, here we are taking the solar power and here we are taking the grid. And the thing is, this PV source, nothing but the solar source, shares the common ground with the grid, okay, so that it can eliminate the leakage currents. And here we are using the 5 switches, 1, 2, 3, 4, 5, okay. And here we have some auxiliary capacitor. This is a additional capacitor we are taking, and this diode and this inductor with this switch make a buck boost converter operation, okay. And these 1, 2, 3, 4 switches will make a inverter operation, okay. And this is the grid inductor, nothing but the filter inductor we are taking here. So this is the simple circuit we are taking for our project. So here there is a no bulky stages. Here we are taking all the operations in single stage, in single circuit only. That is our main theme. single stage buck boost transformerless inverter. So in this single diagram only we are having buck boost converter and inverters and a whole this solar to this grid connection. That's why our proposed system has low switching losses and low leakage currents and less size when compared to conventional one and more efficiency, because if you reduce the losses then efficiency will increases, right? Now let's look into how this whole system works. Means we have number of modes, right? So let's look into that modes. So this is the switching mode operation table. Okay, here we have the 4 mode of operations, A, B, C, D. Okay, in first mode of operation, this is the first mode of operation. Here we have the positive off cycle, because in alternating current we have the 2 off cycles, positive and negative, right? So if you take the positive off cycle, switch 1 and 3 and 5, 3 switches are on. So that is the first mode of operation. So the circuit will be like this. Okay, this is the first operation mode. Here switch 1, 3, 5 is on. Switch 1 means this, right? And switch 3 means this one. And switch 5 means this one. So then current flow will be like this. This solar panel and this inductor and this switch S1. And the outer loop will be like this. This grid to this switch S3 and auxiliary capacitor and goes to switch 5 and goes to this inductor. This is the current path that red line indicates. Okay, so this is the first mode of operation. So in second mode of operation, this is the second mode of operation. Mode B is the second mode of operation. Here switch 5 is on and diode D is on. Okay, this diagram shows the second mode of operation B. So here only switch S5 and diode D is turned on, means this diode and this switch S5 is turned on. Okay, and here this solar panel is completely turned off. If solar panel is completely turned off, then how we give power to this grid? By using this auxiliary capacitor. That's why we are taking this one. Okay, so in first mode of operation we charge this capacitor. In second mode of operation we don't have the solar panel. Then whatever the voltage stored in capacity, then that will goes to the load. That is the point why we are taking this auxiliary capacitor. But here actually switch 2 is off condition, but that anti-parallel diode will be conduction. That's why we are taking the anti-parallel diode to our switch IGBT. Okay, so that red line indicates the current directions. That's it. And coming to the mode 3, so this is the mode 3 operation, nothing but mode C. Here switch S1 and S2 and S4 are on condition. Okay, means S1 is on, S2 is on and S4 is on. And here the current flow is like this. This is the inner path like a solar panel and switch 1 and inductor. And the outer loop is like this. This grid and through inductor switch S4 and goes to this auxiliary capacitor and goes to switch S2. These are the 2 paths in mode 3. Okay, and coming to the mode 4, this is the mode 4 operation, right? That nothing but the mode D. Here actually this third and fourth mode have the negative half cycle. That's why the current directions are reversed. So in fourth mode of operation, we need to turn on the switch S2 and diode D only. That's why this diode D and this S2 will be on. So here solar panel is off condition. So the power is goes to grid from this capacitor C. Here S2 is on and diode D is on. That's it. But this switch S5 is in off condition, but this anti-parallel diode can make a closed path. That is the use of anti-parallel diode. So this is the 4 mode of operation we are having here. But here we are taking the switches like IGBT, right? You can take the IGBT or MOSFET, whatever it may be. But that is in bidirectional switches, means controllable switches. So to turn on, to turn off these controllable switches, we need to give a pulses, right? Pulsating signals, nothing but the gate signals. To turn on, to turn off this MOSFETs are IGBT. Okay, so for that purpose in our project we are using the simple sinusoidal pulse width modulation technique. We have so many pulse width modulations, but in our project we are using the sinusoidal pulse width modulation technique only. What is this sinusoidal pulse width modulation? How this technique will make a switches on and off? Just take one simple sine wave, right, and take another wave, nothing but the one carrier wave, like anything. But in our project we are taking the triangular wave. Okay, take the triangular wave. You can take trapezoidal, sawtooth, whatever it may be. Okay, but in our project I am taking the triangular wave. That's it. In sinusoidal pulse width modulation we always take this sine wave as the reference wave. That's why this pulse width modulation have name as sinusoidal pulse width modulation. Here in sinusoidal pulse width modulation always take a sine wave as reference wave. Okay, and coming to the next signal, this is the triangular wave, right? This is a carrier wave. Okay, we can call it as a reference wave, and this triangular wave we can name it as a carrier wave. So to turn on, to turn off the switches, Now we can give the conditions. Whenever the reference wave is greater than the carrier wave, then we can give the condition is switch is on. If our reference wave is less than the carrier wave, then we need to turn off the switches. Like this, we can give the conditions to our waveform. Okay. Now at this point to this point, whether sine wave is more or carrier wave is more, obviously this carrier wave is more, right? So at this point to this point, carrier wave is higher, means second condition is true, means here switch is off. Okay, and this point to this point, so here reference wave is more or carrier wave is more, obviously this reference wave is more, right? So that's why condition 1 is true, then we need to turn on the switch. So at this condition only switch is on. Okay, so like this we can generate the on off pulses to our switches. Off and again on, again off, again on, again off, again on. Like this we are taking the pulses to our switches. This is the simple sinusoidal pulse width modulation we are using here. Okay, to turn on and to turn off the switches. And the main thing you need to know is this diagram will make a pulse width modulation technique for our circuit. Okay, in our circuit we have the 5 switches, right? So S1, S2, S3, S4, S5. So we need to give 5 pulses. If you observe switch 5 and this switch 2, whenever this switch S2 is off, then S1 is must on. So here S2 is off, then S5 is on. Here S2 is on, then S5 is off. Here S2 is again on, again this S5 is off. Means these two are totally opposite. Means whenever this switch S2 is off, then S1 must be on. Okay, that's why if you give this reference wave as Vm sin omega t, so here we are taking the reference wave as Vm sin omega t and give it to the comparator to compare the greater and less than conditions and give this output pulses to switch S5. Okay, and another pulse to switch S2, and here we are taking the NOT gate here. Why NOT gate? Whenever the input is 1, then output is 0, right? Whenever the input is 0, then output is 1, right? That is what we want for S2 and S5 switches. Whenever S2 is 0, then we want S5 as 1. Whenever S2 is 1, we want S5 as 0. That's why I am taking the NOT gate here. So like this, take the reference wave as same to all, and here I am taking the VTR, means triangular wave. V triangular wave, that is nothing but the carrier wave, right? So we compare this carrier wave and this sine wave, give switch pulses. But here in switch S4 we are taking the invert symbol. Why? Because S4 switch is only on in negative cycle only. This is the negative half cycle, right? So here it is the off in positive half cycle in 1 and 2. Only it can on in C mode. So whenever you have the invert that one, then you will get the conversion of positive to negative. That's it. That's why I am taking the invert here. Okay. Now this table shows the comparison between our proposed buck boost transformerless inverter to other projects. Here in our project we are using the number of switches as 5, but conventional projects they are using the 6 switches. So we are having the less number of switches, right? And number of diodes also we are using the only 1, but in other projects they are using the 2 diodes, and number of inductors we are using only 1, and some other projects they are using 2, and number of capacitors we are using only 1. Okay, others also using the same thing, but we don't have the DC offset, and others have DC offset also. That is the drawback of others, and our advantage is we don't have the DC offset. And coming to the total harmonic distortion, we have the low THD, only 3.31 we are getting at the output. Okay, and remaining parts have the more THD values. So that is the main thing why our project is having the more efficiency and low losses. Now let's connect our project in MATLAB to observe the results. Okay, so before that one we need to know about the ratings of our project, right? Here we are taking the power rating as 300 watts and switching frequency as 10 kHz, and we are taking the input voltage as 75 volts. Okay, that is the input voltage we are taking for solar. Okay, and input inductor is 115 microhenry. So here we have the input inductor, right? This cell indicates the input inductor. So the value of this inductor is 115 microhenry, and the rating of this auxiliary capacitor is 50 microfarads. So this is the auxiliary capacitor, right? So this value is 50 microfarads, and output filter value is 1 millihenry. Near to grid we have the some inductor LG. Okay, this is the grid inductor, then that value is 1 millihenry, and filter capacitor is 10 microfarads. Below the solar panel we have the filter capacitor, so this value is 10 microfarads. Okay, that's it. These are the ratings you are taking in MATLAB. So take the same ratings in your MATLAB. That's it, you will get the exact results. Okay, now open your MATLAB. So here we need to connect our circuit. Okay, go to library to take the elements. So this is the library, Simscape, Power Systems, Special Technologies, Fundamental Blocks. Here you will get the all the elements. First of all, take the elements what you need. Here this is the our circuit, right? We need a capacitor and solar panel and IGBT switch and also inductors and some voltage source for a grid and inductor also, and we also need a ground terminals, okay, and diode also. So this is the design of circuit. And coming to the control part, we need a one constant sine wave. We can take it from the this grid, okay. Vm sin omega t is the voltage of the grid, okay. No need to take the another sine wave, and we need to take a some carrier wave, right? Triangular wave we can take, and one comparator and one NOT gate and one invert symbol and one ABS modular and this go to blocks, okay. From and go to blocks we need to take. In electrical sources we are having the single phase AC voltage source, take it as a grid, okay, and take the RLC branch in elements and also take the ground, we also need that, right? And go to measurements, take the voltage measurement and current measurement to measure the voltage and currents. They will act like a ammeter and voltmeter. And go to power electronics, take diode, we also need a diode and we also need a 5 switches, okay. So take IGBT with anti-parallel diode, okay. Here you will get that one. And our main theme is take a solar panel, right? So go to renewables. In solar you will get the solar PV array. Go to fundamental blocks, take the power GA block. Without this one we can't run the our circuit, okay. In commonly used blocks, take the constant to give the irradiation and temperature to our solar panel, and also take the scope. And go to signal routing, take the from and go to blocks to give the access to our switches, okay. And go to math operators and take the ABS. Why? Because here we have the ABS, right? And take the invert and comparators also. And go to logic and bit operator, take the logical operator to take a NOT gate. Here we have the AND gate, no need about that. After we can modify it as a NOT gate, okay. Take this logical and bit operator and go to math operator and take a gate. And go to sources to take a repeating sequence. Here in carrier wave we have a triangular wave, right? So for taking triangular wave, take the repeating sequence, okay. That's it. These are the things we need for our project. Now here we have all elements. Take each one and cut the circuit as per our circuit diagram. Here we have auxiliary capacitor first. Take the auxiliary capacitor, okay. From this series RLC branch you can take the capacitor also and take C only. What is the rating of capacitor here? Here I already mentioned the parameters here, okay. This is the ratings. What is the auxiliary capacitor rating? 50 microfarads, right? So take the capacitor as 50 e power minus 6. That's it. This is the 50 microfarads capacitor. That's it. After that we have a solar panel, right? So take the solar panel also. And in solar panel we need to give the irradiation and temperature inputs, right? So take the constant to give the irradiation. I'm taking irradiation as 1500 and take the temperature like 25 degrees. Okay, take the 25 degrees. Take the switch IGBT. So take this one, connect it to the this positive. And here we also have diode and inductor and switches, right? So connect the circuit like this and take the diode here and take capacitor here for ground terminal and take the current measurement to measure the current and take the inductor also, inductor, and give this inductor value as what is the inductor value. So here input inductor is 115 microhenry, right? 115 e power minus 6. That's it. And connect to the current measurement like this, okay. So here current measurement is nothing but the ammeter, so that's why I'm taking the series here. Now connect this diode to this capacitor, okay. So connect like this to measure the voltage across the capacitor, okay. Now take the another switch and give it below and connect it to the inductor and this capacitor and take the remaining 3 switches also. Total we have the 5 switches, right? So take like this, okay. And take the grid here and we also need a some inductor for grid also, okay. Take the inductor also and connect. So to measure the grid current, take the current measurement series to your grid and give it to the switches. To measure the voltage across this grid, take the voltage measurement also and connect across the grid. Connect like this, okay. And take the ground, connect for this grid and also connect the this input solar also and connect this switch to this one. That's it. This is the our complete circuit diagram, okay. Now take the go to blocks and connect to the each and every voltmeter and ammeter and you can name it as a capacitor voltage VCA, grid voltage like VG and grid current like Ig, you can name it as. Okay, and this inductor current nothing but IL. Okay, you can also take the inductor current as IL. That's it. And we also give this switches to pulses, right? So take the from block to give this switching pulses for this switch and for this one to all IGBTs, and you can name it as a S1, S2 like that. For this S2, S3, S4, S5 like this you can give. Okay, and don't forget take the all inductor and capacitor ratings as per our table only. Okay, circuit diagram is completed. Now coming to the switching pulses part. Take the from block and name it as a VG, and we can give this VG to comparator. Okay, nothing but the relation operator. Okay, give it to the relation operator, nothing but this greater than and less than conditions. Here we have the repeating sequence and give it to the this one. That's it. And after generation of these pulses you can give it to the switches. Okay, so take the go to block and give it to the switch S5, and take the NOT gate here and give it to the switch S2, because these two are opposite. Okay, for remaining three switches also take the three reference. Okay, and take the three less than and greater than conditions also, and take it as a reference and take it as a carrier and give it to the remaining three switches. Here we have the inverter, right? Here I am taking the gain as -1. That's it. It can act as a invert. And take the ABS here. Why ABS? Because here in our control diagram they are giving the ABS. That's why I am taking here. Okay, and give this ABS to this one and this one like this. That's it. Now give this all switching pulses to our switches and name this three switches as S1, S4, S3, right? So this is S1, this is S4, and this is S3, right? That's it. Like this you can take the all switching pulses. Now to see the measured voltage waveforms, take the from blocks. Okay, so if you want to see the grid voltage, name it as a VG. If you want to see the grid current, take the another from block and name it as a IG to see the grid current. Okay, and if you want to see the inductor current and capacitor voltage also, take another from block and name it as a IL to see the inductor current. And if you want to see the auxiliary capacitor voltage, take another from block and name it as a VCA. Okay, now give this all to scope to see the waveforms. But here we have the only one input. So go to scope, go to configuration properties and take this number of input ports as 4 and take layout as 4 layers. That's it, and click on OK. Here you will get the 4 different axes, right? Give it to 4 from blocks. So here you can able to see the all 4 waveforms. That's it. Now run your circuit to see the waveforms. After completion of running, click on scope to see the waveforms. That's our waveforms, right? First one is grid voltage, grid current. Those two are AC, right? And this one is inductor current. If you want to zoom, just zoom it. Then you can able to see just charging and discharging like that. So this is the auxiliary capacitor here. Here also you can get the charging and discharging states. That's it. These are the waveforms and this is the our final circuit. So if you want this project, just contact me. And I also provide the base paper of this project in description. You can go through once. If this project is perfect suits for you, then contact me.